finished up chapter 9. We've done some of the topics in chapter 9, but we got to go back and pick up a few extra. So what we're going to do today is non-quadrilateral, non-triangle polygons. So like pentagons, hexagons, octagons, all those other things. How do I find the area of those? Okay, so there's some vocabulary you need to know. The first one is the center of a polygon works like the center of a circle. It's the point that is equidistant to all the vertices. So it's the same distance to here to here, here to here, here to here, there to there. Okay, that's the center of a polygon. Okay, equidistant to all the vertices. The central angle, just like a central angle in a circle, the central angle is vertex is at the center, okay? But like a circle doesn't have corners, so the central angle can just be anywhere. In a polygon, because there are vertices, the central angle's ends intersects those vertices. Okay? So in a six-sided figure, how many central angles can I have? 6, right? In a pentagon, how many central angles can I have? 5, right? But and it also works like in a circle, the central angles, by the fact that if I take all these angles added together, how many degrees do I get? 360. Okay? And so, since this is a regular polygon, what's regular mean? Right, the sides and angles are equal. So since this is a regular polygon, it means that all these angles would be the same, right? All right, so how do you think I find the degree of that central angle? Come on, guys. How do I find this center? How would I find? There's 6 angles. The whole thing's 360. How can I find out what each one is? Yeah, take 360 and divide it by 6. Okay? N is number 5. All right, so how many is each degree? How many degrees is each angle? How much? 60, right. This central angle 60, this central angle 60, this central angle 60. Okay? All right, find out the central angle of that pentagon. Take a minute and figure out the central angle of the pentagon. Okay, so how did you find that out? Hillary, what did you do? Right. If here's the center, and I connect all the vertices, there are 5 angles. Each one is exactly the same measure, so I take 360 divided by 5, which is what? 72. Good. All of these would be 72. All right? Now, let's talk about these angles here, because obviously if I add in the side of the angle, I make a triangle, right? What kind of triangle is that? Equilateral. Why equilateral? Because all angles are 60. How do you know? You should trust it. I do implicitly, but I need some proof. Why would all the angles be 60? You said they were all 62. Why would they all be 60? Well, sort of, we'd have to prove it was all 60 first before we could say it was a 30, 60, 90, right? Right, if that one's 60, that's what we know. Why would those be 60? I'm sorry? Why? It's an isosceles triangle. Why would it be isosceles?
Because from the center to the work, because the length going from center to the work inside is equal.
Exactly. The distance remember we said the distance from the center of the shape to its angles, from here to there, from here to there, those are equal. So this makes this an isosceles triangle. What do you know what the angles of an isosceles triangle? They're the same. So if I've already used up 60, how many degrees do I have left? 120, divide that by 2, and you get 60. Okay? Now, so this makes it an equilateral triangle. Does that make this one over here an equilateral triangle too? No? Yes?
No. All the sides are all angles are going to be 60.
Okay, what kind of triangle is it? It's isosceles. Right, it's isosceles. Could I figure out these angles?
Yes.
How? Right, which is what? 54?
Yeah.
Okay. Now, the last vocabulary word I want to talk about is an apothegm. Now, when I went to school a long time ago, we said it apothegm. So sometimes you'll hear it referred to that way, but I think nowadays most people say apothegm. Okay? And the apothegm is the line from the center of the shape perpendicular to one of its sides. Okay? And so this is an isosceles triangle. What does that make this line? What's one thing it can be? Nope, not a hypotenuse. That'd be over here and over here, right? What would that be? What can we call that? An altitude. What else? Yeah, a height. Perpendicular bisector, angle bisector, and the median, right? Remember they all four go together? Whenever I have an isosceles triangle, that line becomes angle bisector, perpendicular bisector, altitude, and median. Okay? Which we're going to use a lot of those characteristics when we to try to find different missing pieces. All right, so if that's a perpendicular bisector, that means these two pieces are the same, right? These two edges, these two halves of a side have to be the same measure. And it's an angle bisector, so that means I've divided that angle in half. So that's 30 and 30. Okay? And what if I want to find the area of that whole shape, couldn't I find the area of this little triangle right here and then multiply it by 12, right? Aren't there 12 of them? 2 here, 2 here, 2 there, 2 there, 2 there, 2 there. So 12 altogether, right? So I can find out the area of that one and then multiply it, okay? Or I could find, so this is, I think, Prashad said this is also the height. So if I could find this, the length of this side times the height, I could do 1/2 base times height and then multiply it by 6, right?
Well, if you had the area of that, can you just multiply by 2 and then multiply that by 6?
Right. Right. Same thing, yeah. Multiply by 12, same as multiply by 2 and then multiply by 6. Right. So there are kind of two ways to find the area of this shape. One of them is to find the area of one of these triangles and then multiply by however many little triangles there are. Like there are 12 in this shape, but how many would there be in this shape? In the pentagon? 10. Yeah. And in an octagon, there'd be 16. Okay, so one way is to find that little area and then multiply. Sometimes that's the easiest way. Okay? And then sometimes, let me show you, we have a formula, like on your green formula sheets, there's a formula for non-quadrilateral polygons. And let me show you how we got it. So we said you take the area of this triangle and you multiply it by the number of sides, because there's one triangle per side, right? Okay? So 1/2 times the apothegm, which is the height, times the length of the side, which is the base, that's the area of the triangle, right? and n is always the number of sides. So you take the area of the triangle times the number of sides, and that should give you the area of the whole thing. Well, if I took the length of this side, which is s, and multiplied it by the total number of sides, what does that give me? The perimeter. Right. So all they did was, to get this formula for a polygon, is they said, I'm going to take the area of the triangle times the number of triangles there are, but I'm going to rewrite it. I'm going to say that s times n, the length of the side times the number of sides, is the perimeter. So instead of saying n times 1/2 times a times s, all they said was it's 1/2 times the apothem times the perimeter. And that's how they get that formula. And sometimes that's easier. Sometimes it's just easier to use that formula. Okay? So I want you to know both ways to do it so that you can calculate, you can do it either way depending on what information you have. All right, so let's do one. Okay? I have this central angle here. The apothem is 14. All right, and it makes a right triangle. Right triangles are the superheroes of geometry because there's so many things they can do for us, right? So if I know the apothem and I know this is a six-sided figure, what else do I know? What do we calculate up here? What do we calculate? Yeah, we calculate the central angles. So I know that that angle is what? 60. Okay, and I know that since it's an angle bisector, this is 30 and 30. Okay, so let's talk about the ways we have of finding missing pieces in a right triangle. What's one way you can find missing pieces? What's one way you can find missing pieces of a triangle, right triangle? What's one of the tools we have? Can we help her out? What's something we can use? I'm sorry? No. Pythagorean theorem is one. Right. What's another one? SOHCAHTOA, right? We can use trig functions to find missing pieces. Also, this is a 30, 60, 90 triangle. Can't we use special right triangles to find missing pieces? Okay? So I can use any of those tools that is handy to find out missing pieces and missing sides. So since this is a 30, 60, 90 triangle, I'm going to use special triangles. Okay? So since 14 is the opposite of 60, is that x, 2x, or x squared root of 3? X squared root of 3. So I know that 14 is equal to x squared root of 3. So if I'm trying to find this piece, that would be x, right? So to get x, I would divide by square root of 3. Those would cancel. Now, normally we would work this so that we would get an exact answer, but really I need the actual number for this. So I am going to plug in my calculator 14 divided by square root of 3. Yeah, I don't get a choice. Which is 8.08. Okay? So I know that this side is 8.08. Now, what I'd like to do is, let's divide the class in half. You guys find the area of this hexagon using the triangle method. Find the area of the triangle and then multiply it by 12. You guys, on this half, use the formula, 1/2 times apothem times perimeter. Okay? And let's see if we get the same answer.